Okay, good afternoon. Can you hear me?
Yes.
Hello.
Yes, sir. Yes.
Yeah, okay, very good. Very good. So let's start today's lecture. Some people wrote back to me saying that they would like me to go a little more slowly and to recapitulate what we have done in the last couple of lectures. So I thought I'll continue with the new lecture today. It's a new topic, but it's similar to what we have done. And next week, I'll recapitulate what we have done till now, including today's lecture. So that is a better plan because it will show me show you the analogy between what we have been doing and what we are going to do today. Okay. So if you have not understood anything from the previous lectures, there is no need to worry because we are starting something completely new. Okay, fine. So let's start. Let's take a prime number P let's fix it. Now I'm going to take a finite field K of characteristic P, and Q is going to be the number of elements in that field. I denote by B the ring of polynomials in one variable over this little field K. Now this is to be thought of as analogous to the ring Z. One of the similarities between these two rings is that both of them are principal rings, right? You know that every ideal in Z is generated by a single element, and so is every ideal in the ring KT. So let us denote by Bn the quotient of B. I'm calling it B just in order to save space. The correct name is KT. So Bn is B modulo T to the n times B. So that this is an ideal, of course, of the ring B. And this Bn is analogous to the rings An, which we had earlier, which was, An was equal to Z modulo P to the n Z, right? And of course, because of the inclusion of ideals like this, every multiple of T to the n plus 1 is of course a multiple of T to the n. Because of this inclusion of ideals, we have this map phi n, which is a homomorphism of rings. Okay, so actually what we have is a whole inverse system here. You have B1, then a map phi1 from B2 to B1, then a map phi2 from B3 to B3 to B2, and so on, right? It's an inverse system of rings, right? And I'll denote by O. Now this is supposed to be a Gothic O. I don't know how to be written something like this. It's a German O. So in order to distinguish it, I'll draw two lines below it. And another notation, the more standard notation, is K double bracket T. These are parentheses, these are brackets, and what we are using are double brackets because we are not talking about polynomials, we are talking about formal power series like this. So a typical element of this ring O is A0 plus A1t plus A2t squared, and so on, ad infinitum, all the way up to infinity. I mean, doesn't stop. I don't know what has happened here. Okay. Anyway, so these AIs are in this field FP. Compare this with what happens for ZP. You know, this ring O is supposed to be analogous to the ring ZP because we got it from the ring B by a process of completion, just as we had got ZP from Z by completion, right? So in ZP, every element could be written A0 plus A1P. First of all, this is not an indeterminate, this is an actual number. Here, this T is an indeterminate. A1P plus A2P squared, and so on, all the way up to infinity. So the first difference is that you have an indeterminate T here, whereas you have the number P here. And the second difference, a big difference, is that the AIs are elements of this field FP, whereas here, these AIs are just elements of the set 0 to P minus 1. This set is, of course, not a field at all, and it's not even a group or anything, it's just a set. But it's a set of numbers. Anyway, so the first observation to be made about this ring is that it's integral, which means that if I take one element which is non-zero, another element which is non-zero, then their product is non-zero. That's what I want to show. So take an element A, which it will look like this. It will be AM plus T to the M and so on for some M in N, where, yeah, I should have said AM is non-zero. Similarly, I'm taking a B which starts at Bn T to the N, and this Bn is non-zero. Then what is the product AB? It is going to be this plus some higher order terms, and this coefficient is non-zero because AM is non-zero and Bn is non-zero, and K is a field, so the product of two non-zero elements is non-zero. That was a small proof, but you should, I'm sure all of you can do it for yourselves. Now, the next observation is that just as the ring ZP had a unique maximal ideal, which was PZP, this ring O has a unique maximal ideal, which is T with these two underlined things. So it's supposed to be a Gothic T, a German T, and it's generated by this little t. Just as this P, ZP is generated by P, similarly, this ideal is generated by the indeterminate T. And so this is the unique maximal ideal of this. Another way of saying it is that if I have some element of the ring which is not in this ideal, then that element is actually invertible. Okay? So let's see why this is the case. So take an element A, every element will look like this, and I'm assuming that it's not in the ideal generated by the indeterminate T. And I want to show that it's invertible. So I have to look for an A inverse. This A inverse is also an element of this ring. So I can, I'm looking for an element of this kind. Now, these BIs are, of course, in K, but they are to be determined. These AIs, of course, are given to me. AIs are in K, and they're given to me. This A is given. And why is A not equal to 0? It's not equal to 0 because this A is not in the ideal generated by T. Okay, so these A's are given to me and these B's are the ones which I have to find out. And I'm looking for these B's so that the product is equal to 1. Now, if you actually compute this product and group the terms, then this is going to be the constant term. This is the coefficient of t, and then you're going to get higher order things. So now you compare the coefficients on the two sides. Here, this is 1 plus 0 times t plus 0 times t squared, and so on. So this means that the constant term here is equal, gives me this relation. The coefficient of t gives me this relation, and I get lots of other relations as well. For every power of t, I get a relation like this, right? So the first relation, of course, tells me this relation, gives me immediately that B naught has to be equal to this. And in general, these other relations will tell me that Bn has to be A naught inverse times this. Of course, this is a relation in terms of the other B's, the lower B's. But the lower B's have already been computed. In other words, I'm giving a recursive definition of the B's. You start with B naught equal to 0, B naught equal to A naught inverse. Then B1 is going to be A naught inverse times whatever. You take n equal to 1 here, right? So, yes? Does somebody have a question? Maybe I should. Okay. So that gives you all the B's and you got your A inverse. You solve for this, and therefore we can show that if A is not in the ideal generated by T, then A is actually a unit. Now, what is the quotient of O modulo this ideal? This is obviously equal to K. The field, which is, so O, remember, is K, and then this power series T, and modulo T, of course, this is going to be just little k, right? So there's nothing, I'm not saying anything extraordinary here, right? Okay, and so this ideal is maximal, and this is what we have proved. If A is not in this ideal, then it's invertible. So T is the unique maximal ideal. Okay. Now this is, of course, similar to the fact that PZP is the unique maximal ideal of ZP. And here T, the ideal generated by T, is the unique maximal ideal of this ring O. Every non-zero A can be uniquely written as some power of T times a unit. Okay, so A is non-zero means that A can be written like this, where this AN is non-zero, and then of course this A is, you can take this T to the N outside and you'll get this thing inside. But this thing inside is, let's call it U, and this is invertible. It's in O star because this is non-zero. This is what we had proved here, right? If your A naught is non-zero, then you can find this B. Then A is in the units. Okay, So how about the uniqueness? I mean, can you write if you have t to the n times u, where n is in n and u is in O star, if this is equal to t to the m times v, where m is also in n and v is in the units, then we want to conclude that m is equal to n and u is equal to v, right? So this is absolutely obvious, and there's nothing really to be proved. You just cancel out the t's wherever they are, and then you'll get a unit on one side, so the other side also has to be a unit, and therefore m and n are equal. And if they're equal, you just remove them, then u and v have to be equal as well. Okay. So the fact that you can write every element a as t to the n times u, n is a natural number, u is a unit, means that I can define this vt like this. Vt is a map from O to this monoid n union plus infinity. It's a monoid. I can add things here, right? If both of them are here, then of course, you know how to add them. But if one of them is plus infinity, or so a plus plus infinity is equal to plus infinity for all a in n union plus infinity, right? This is the convention. So this is a monoid, and what this vt, I mean, vt gives you the exponent of t if a is non-zero, and therefore you can write it as t to the n times some unit. But if a is equal to 0, you define vt of a to be plus infinity. And this vt is a morphism from this multiplicative monoid. O under multiplication is a monoid. So vt of ab is equal to vt of a plus vt of b. So it's a morphism from this multiplicative monoid to this additive monoid. And of course, inside this, the ideal t is characterized by those vt. I mean, so this vt of a is called the valuation of a. So a isn't the ideal t if and only if its valuation is strictly positive. Okay, and here is the important property which really makes it into a valuation, which is that vt of a sum is at least it's bigger than the smaller of these two. The vt of a sum is always bigger than this smaller of the two summates, the two terms. Okay? And moreover, actually, you have equality in this if the two valuations are really different. If they are not the same. If they're the same, then you can have strict inequality here. Otherwise, if they are different, then you always have equality. Not you can have, you always have equality if these two are different. But when they are the same, you may have strict inequality. It's not forced, but it may happen. Okay. So next, we are saying that every ideal of this ring O is generated by t to the n for some n. Just as every ideal of Zp is p to the n Zp is equal to p to the n Zp for some n, non-zero ideal, okay, right? So let's take an ideal, let's take this ideal, and then it's non-zero. So Wait a moment. Maybe I should say union infinity. Yeah. So if I take the VT of that ideal, that's going to be a subset of this n union infinity. And it's not, the image is not just infinity, because Vt of A is equal to infinite plus infinity if and only if A is equal to 0, right? Now, by hypothesis, this ideal A is non-zero. So there is a non-zero element, and therefore there's some element in the ideal whose valuation is in n. So whenever I have a subset of this, there's some element which is the smallest element. So there has to be some element x in the ideal such that its valuation is the smallest possible in this subset. Okay? So this x, of course, can be written as, if n is the valuation, then it is t to the n times u for some unit. Then t to the n is going to be this. Now, x is in the ideal, and this is in the ring, so t to the n is in the ideal. So the ideal generated by t to the n is, of course, contained in this ideal. Now I want to show that conversely, this A, this ideal, is contained in this ideal t to the n. So take some y in the ideal. This is not supposed to be O, this is supposed to be A. Take some y in the ideal A. We have to show that y is a multiple of t to the n. In any case, what we know is that the valuation of y is greater than n, because the smallest possible valuation is n. The smallest possible valuation of an element of the ideal A is n. So the valuation of this element y has to be at least n. So we can write y equal to t to the m times v, where m is greater than n and v is a unit. Then, of course, this y can be written as this thing, this expression here, and that means, so it's a multiple of t to the n. So y belongs to this ideal generated by t to the n, and therefore A is contained in this ideal generated by t to the n. And since I have already proved that t to the n, I mean, this is where we have proved. This is where we have proved that this t to the n is contained in the ideal A, right? Yeah, here it was. And now we have proved this, so we get the equality of these two ideals. Okay? Fine. Now, so we have seen that this is an integral ring, so I can take its field of fractions. So this K, of course, will correspond to, meaning it's analogous to the field QP, because O was analogous to the ring ZP. And just as there, QP was obtained from ZP by just inverting T, not T, P. Similarly, this K, now, similarly, this K is, this is our ring O, right? This is the same as the ring O. K is obtained from O by just inverting the indeterminate T. And the notation for capital K is little k power series T. These are sometimes called, what are they called? Laurent series. Right? Because, okay, so the difference between these low round series and the usual power series is that in a low round series is of this form, an t to the n plus an plus 1 t to the n plus 1 and so on, where this n is allowed to be in z. Whereas for a formal power series, the n has to be, earlier it was in this n, right? And these coefficients ai's are of course in the finite field, little k. So just as every a in the ring could be uniquely written as t to the n times u, where n was a natural number, here every non-zero a can be written as t to the n times u, where n is now allowed to be an arbitrary integer and u remains a unit in the ring, okay? So if I define the valuation of such an a to be n, I'm just extending. This extends the map Vt from the ring O to the field K. And of course, the values also are allowed to be integers now. So Vt is a map from the field K to this additive monoid. And it takes, so maybe we'll come to that shortly. And inside this K, the ring O is characterized as consisting of those A whose valuation is positive. So the important properties of this valuation on the field K are, first, that it's a morphism of multiplicative, from the multiplicative monoid K to the additive monoid Z union infinity, which is a very fancy way of saying that Vt of a product is the sum of the Vt's. And this is the basic property which makes it a valuation. The Vt of a sum is bigger than the smaller of the two valuations. And you have equality if these two valuations are really different. Right?
Sir?
Yes.
So like, why are we taking here K to be a finite field? I mean, all of this should work with any field, right?
Yeah, that's right. That's right. Because later, yeah, you are absolutely right. Many of the things I'm doing today will work for K, an arbitrary field. Even characteristic P is not required. But the case which really interests me is when K is a finite field of characteristic P, because the rest of the lecture, we'll see that this is more similar to ZP and QP and so on than the case of a general coefficient field. For example, one of the reasons, you had this ring O and you had this unique maximal ideal. And what was this equal to? This was equal to K. And what was the thing in the case of ZP? This was equal to FP. So these things are called residue fields, right? This is the residue field of ZP, and this is the residue field of O. Now the similarity is that in both cases, the residue fields are finite. That makes a lot of difference in many places. So that's why I took K to be a finite field, because I want the analogy with ZP to be as close as possible. And we'll see later, I mean, today that it's very important. It works perfectly when you take K to be a finite field. Yeah, so till now, I mean, we have not used it much.
Okay, thanks.
Yeah. So now you take this UN. So of course, these BNs are quotients. You have a ring A, and what is BN? BN is just O modulo Tn, where Tn, remember, T is the ideal generated by the indeterminate T. So Tn is the ideal generated by T, the nth power of the T indeterminate. And this homomorphism of rings gives you this homomorphism of groups from the units of O to the units of the ring Bn, or the multiplicative group of the ring O to the multiplicative group here. So you can check that this is surjective, and I'm calling the kernel Un. So what is it? It's basically 1 plus T to the n, because that's, well, these are the elements which go to 1 here, right? Okay, so yeah, here, this equality shows that this map is surjective, the map from to Bn is surjective. Yeah, this is kind of completely obvious. Yeah, and the special case n equal to 1 is this, and of course every element, every unit can be written as a non-zero element of k times an element which goes to 1 under reduction modulo t, right? So this is supposed to be analogous to the fact that Zp star is here. Yeah, so as I said, there are lots of similarities between the ring O and the ring Zp. Lots of similarities, but one difference is that the residue field K is contained in the ring, whereas here the residue field is Fp is not contained in Zp, right? Now, where is it gone? It's not contained in Zp. What you have is, and therefore Fp star is, I mean, in some sense, it's not really contained inside Zp, but what you have are two substitutes. You know, this is in bijection with some R, which actually is contained in Zp, and this R, remember, was the roots of T to the P minus T. And this is contained in R. This is in bijection with R star, which were the roots of T to the P minus 1 minus 1. And this actually is contained in Z. So this is another notation for this R star, what I'd called R star earlier. Omega, so omega is the map from Fp to Zp, and which takes, yeah. Do you remember this map? Maybe I had not given it a name, and the real name is Teichmüller representative, or the okay, representatives. Omega x is the Teichmüller representative of x. So this is in Zp. Anyway, let's come back to our O star. The units are just little k star times U1. Okay, so in the case of Zp, we hardly ever made the assumption that P is different from 2. We sometimes had to treat these two cases separately, but both these cases were allowed. Here, it's very important to make this assumption that P is different from 2 for many of the things I'm going to do today. And it's a completely different theory. The case P equal to 2 is a different theory, which we will come to later. So not today, but this is sort of the assumption throughout today. So take a prime which is odd, and if I have an x in U1, then there's a unique y in U1 such that x is equal to y squared. Yeah.
Sir,
Yes.
this FP of that power series ring over this finite field, this is profinite, right?
It's a profinite ring, this FP power series.
Power series over FP.
Not this one, but yeah, the power series ring is profinite, yes, yeah.
So if I change that field from finite, I'm not getting profinite.
Of course, it's not profinite, yeah.
Yeah.
No. If you, for example, see power series T, it's not a profinite ring.
Yeah.
No.
No, someone was asking about that, why you are choosing FP, not any field.
Yeah, yes. So, well, the real answer is that some of the things might work, but you'll see, it's...
Sir,
yes.
sir, do people see the inverse image of infinite rings or infinite groups to make means to see the means it will still form means it has to satisfy those rules means okay if you have
Yeah, of course. Yeah, you can try to do what you feel like doing, except that for one of the properties, you might not have all the properties. We have been using, for example, the fact that for a finite field K star is finite and it's cyclic.
Yes.
And K star modulo squares is a group of order 2. So this is isomorphic to Z star, etc. We have been using such things. And they will not hold if you have an arbitrary field, little k, right? So it's very important that the residue field is finite. Now, there are many things which work if you allow the residue field to be perfect. And finite fields are perfect. Fields of characteristic 0 are perfect. Many things will work for arbitrary residue fields, etc. And sometimes you have to modify them if the field is not perfect, the residue field is not perfect. Let's not get into this. Let's first learn these things for when the residue field is finite, and then we can try to explore what happens if you remove this hypothesis. The closest analogy with, you see, our approach has been the following. It's a sort of constructive approach. We start exploring from what we already have. We have Z, and then we have prime numbers, so we have this ideal PZ, and then you have this inverse system which arises from the fact that you have this sequence of ideals. So that gives you the inverse system, and that gives you ZP. So it was a natural way in which this ZP arose. An abstract approach or another approach would be, let's just write down some axioms and try to just work from those axioms. That's also something which can be done. Then you have to develop the theory of valuations and, for example, I've been calling this VT, etc. valuations, but I've not told you what a valuation is. Maybe Supriya did it in one of our tutorials, but what we are doing is starting from concrete things and trying to build up a theory. Okay, so there we go. So let's continue. So if I have a y in U1, then it's always a square. In fact, there's a unique, no, not y in U1. It's the x which is in U1, then there's a unique y such that x is equal to y squared. Okay? So in the case of ZP, we did something similar. If P were different from 2, and we did it using Hensel's lemma. And for P equal to 2, we did it for x in U3, not in U1. If x is in U3, then it's a square. Okay, so that's, I point out that difference. And that is why this here also, you are taking P to be different from 2. And you are saying that for every x in U1 is a square. So here again, you can either formulate and prove an analog of Hensel's lemma. But it's much simpler to just take your x, write it like this. These xi's are in the field K. And you look for a y with these yj's in the field K, such that this equation holds, right? So these x1, x2 are given, and y1, y2 are the things that we are looking for. So if y is equal to this, then what is y squared? It's given by this. You can expand it. You'll get some coefficients for t, t squared, t cubed, and so on. And you want this y squared to be equal to x, which had some coefficients. So if you compare coefficients, you'll get these equations. And using these equations, you have to be able to solve for y1, y2, y3, etc. And it's clear that you can do it, right? I'm sure that you can all write y1 is x1 by 2. And once you know your y1, you can write your y2 to be, it's 1/2 of x2 minus what is it, y1 squared, etc. So there's no other possibility. That gives you, that uniquely determines y. Yeah, so here it has been done. So as 2 is invertible in your field, you can write your y1 to be this, y2, y3, etc. Okay. So now it becomes very important that this is, that K is a finite field. Huh? Because I'm now looking at quadratic characters of K star. So if it's a finite field, this, and of course P is odd, then this is cyclic of even order. Now a cyclic group of even order has a unique quadratic character, because modulo squares, it's a group of order 2. And any two groups of order 2, there's a unique isomorphism between them. So I'm going to call it lambda k. This character, quadratic character, I'm going to call it lambda k. Earlier, I had this quadratic character for fp star, right? Modulo squares. This was isomorphic to z star, and I'd call it lambda p. But now I'm using the notation lambda k. K is this finite field here. Oh yeah, okay, I've already said this. Fine. So, so what's going on? P is different from 2. P is odd. From O star, I have this map to K star. I also have the map to O star modulo squares. From K star, I have the map to K star modulo squares. Therefore, there's an induced map here. And the claim is, where is the claim? I have not written the claim. It's not written here. That's a claim. Yeah.
Isomorphism.
This is an isomorphism. That O star modulo squares is basically the same as K star, not here, K star modulo squares. So how do you show this? This is very easy. O star is supposed to be K star times U1. It's a product of these two groups. And O star is therefore, the squares are therefore going to be the same as squares in K star times the squares in U1. But U1 is equal to U1 squared. So when you, yeah, here it's written. So when you take the quotient, you are going to get the same thing. Okay. So that was the first observation. Now, in any case, I have this quadratic character lambda k of K star. So I can view it as a quadratic character of O star because I have this map. Sorry, I don't know what is happening today. It's supposed to be. You have a map from O star to K star, and therefore you can view this lambda k as a quadratic character of O star as well. Okay. So this is, of course, analogous to what we did for ZP. For there, we had ZP star. From there, you had FP star. Then you had FP star modulo squares, and that is Z star. So this thing here was called lambda p, and this whole composite was also called lambda p. And now I'm defining this lambda k for in analogy. So that's lambda k is you have this O star. From there you go to K star, then you go modulo squares, and that's the same as Z star. Same meaning. This doesn't have to consist of plus minus 1. That you should be careful, because minus 1 may be a square in this field. That you have to be careful about, right? But this, of course, consists of plus minus 1. And so this is being called lambda k, and so is this. Okay, so these are so essentially what we have shown is that O star has a unique quadratic character, which is this lambda k. Now, what are the quadratic characters of K star? Again, it's good if you remember what the quadratic characters of QP star were. QP star, you had nu p, lambda p, and the product of these two things. So here is the analog of nu p. It's going to be called nu t. And what is this nu t? How do you define it? From K star, you have this valuation which takes you to Z. From Z, you can go modulo 2. You get a group of order 2, and that's isomorphic to Z star. So this whole composite is going to be called mu t, right? This is similar to how mu p was defined earlier. So mu p, if you remember, was mu p. How did you define it? You had qp star. From there, you went to Z, and this was the valuation Vp. Then, of course, you can go modulo 2 to get Z mod 2Z. So that's a group of order 2, and there's a unique isomorphism between these two things. And this whole thing is just nu p. Okay, so I've got this nu t here. And for some reason, I'm going to call it the unramified quadratic character of K star. This lambda k was defined only on O star. Now I'm going to define it on K star by taking t to the n times u to just lambda k of u. So you remove the power of t with whatever power of t is there. You just consider the unit part and apply lambda k to that. And that's the lambda k on K star. So lambda k is also a map from K star to Z star, right? So what is the structure of K star? It's Z times O star, right? Because what you have is, right, this there's nothing to explain, because you have this K star, you have VP, which takes you to Z, that's surjective, and the goodness. And the kernel here is O star, and this sequence splits because, for example, I can send 1 to T. So that gives me a splitting, and this splitting gives me an isomorphism between K star and Z times this O star. Okay? So that's why I've written K star equals Z times O star. And this O star was earlier shown to be equal to K star times U1. So if I look at K star squares, that's going to be 2Z here, K star squares here, and U1 squared here, but that's equal to U1 itself. So K star modulo squares is going to be Z modulo 2Z times K star modulo squares. So it's a group of order 4, right? And exponent 2. Exponent 2 means every element is killed by 2. This kind of groups are sometimes called, this group is sometimes called the Klein 4 group, right? Okay. Right. So what are the quadratic? So if it's group of order 4 and exponent 2, then it can have only 3 quadratic characters, and we have found all 3. There's nu t, there's lambda k, and there's the product of these 2 things, right? In other words, this is you see this Hom K star Z star, it consists not just of quadratic characters, but also the trivial homomorphism. Who has stopped screen sharing? Hello, can you hear me?
Yes, sir.
Yes, sir.
Yeah, but can you see the screen? I mean, there's some screen sharing problem. It's not moving, so let me see if, yeah. Okay, so let me see where it is, Zoom. There's some Wi-Fi problem or something. Yeah, just wait a few minutes. Let's see if this Wi-Fi comes back. Okay, otherwise I might have to share the screen here. Let's see. Okay, so this seems to be working now. Can you see the screen now?
No.
No, just wait a moment. I mean,
But we can hear you.
Yeah. It's there now, right?
Now we
Visible,
can
sir.
see. Yeah.
Very good, very good. We will somehow manage. Yeah. Okay, so where were we? I was saying that that's right, that this K has only 3 quadratic characters, and these are the ones. And this group, Hom K star Z star, it's actually an F2 space. An F2 space or an FP space just means that it's a commutative group which is killed by P, vector space over the field Fp. Similarly, this is a vector space, this group here is a vector space over the field F2. And as such, it has a basis consisting of these two elements, nu T and lambda K. Okay, so this is very similar to the fact that Hom QP star Z star as a vector space over F2 consisted of, had a basis consisting of nu P and lambda P as a vector space over F2 when P was different from 2, right? So this is in a perfect analogy. So the person who asked, why do we take K to be a finite field? All this will not work if the field K is not finite, right? So to preserve this analogy with the case of ZP and QP. But this group K star modulo squares itself is, of course, a vector space over F2. And it admits a basis consisting of these two elements, where U is any unit which is not a square. Or, for example, I could take U to be in K star itself, because K now is contained in O. Whereas in the case of ZP, it doesn't contain FP. There's a surjection, but there's no inclusion in the other direction, right? As I just explained. So here are the two characters, nu T and lambda K. And here are the values on the basis elements of K star modulo squares. Nu T of U is equal to 1 because the valuation of U is 0. Nu lambda K of U is -1 because that's how this U has been chosen. It's not a square. Nu T of T is -1 because the valuation of T is 1, which is odd. When nu T of something is 1, if and only if the valuation is even, and it's -1 if the valuation is odd. And here lambda K of T is equal to 1 because after all, this lambda K on, how was it defined? From etc. This was lambda little k, and here T to the N U goes to U, and then this was lambda K. So what would T go to? T would go to 1, so which goes to 1 here, right? So that's the one. Okay. Now we come to the Hilbert symbol, which we had defined for QP, right? Remember, the Hilbert symbol was a symbol denoted like this. It was from QP star cross QP star. It was a map like this. And the definition was simpler if P was different from 2 and slightly more complicated if P is equal to 2. Here, we are not considering the case P equal to 2 at all. We are considering P odd, and we are going to define the Hilbert symbol in exact analogy with this case. So it's going to be a map from K star times K star to Z star, and we'll take the pair A comma B to, this is the notation, A comma B sub T, and that is going to be lambda K of this gamma AB. And what is gamma AB? That is just -1 to the power Vt of A times Vt of B times A to the power Vt of B times B to the power minus Vt of A. That's our gamma AB. It's exactly what it was in the case of QP P odd. So You see, here, this is an explicit definition. It has not been motivated. Meaning, I have not told you why we are defining it, but towards the end of the lecture, it should become clear what use this Hilbert symbol is. So you just have to have a little patience, and we'll see that it's very useful. Just as in the case of QP, we gave the explicit definition. It was not motivated. Where does it come from? But then we saw that it's exactly what tells you. It tells you exactly when this certain equation ax squared plus by squared equals 1, when that equation has a solution in x and y. So we are going to see the same here. But before that, let's look at some elementary properties of the Hilbert symbol. It's symmetric. And that's easy to see because this gamma BA is gamma AB inverse. And it's multiplicative. That's because this gamma itself is multiplicative. And of course, this lambda k is a homomorphism, so it's multiplicative. And you have this property, A minus AT is equal to 1. That's because in this case, gamma A minus A is equal to 1. And of course, we have all these properties for the p-adic Hilbert symbol as well, right? So because of the fact that squares don't matter, the Hilbert symbol is actually a mapping from k star modulo squares times k star modulo squares into z star. Okay, now just as in the case of p different from 2, on qp star you had this Hilbert symbol, and it was completely characterized along with these properties by the fact that AB P is equal to 1 if A and B are both units, and it's not B now, it's P. AP, why is it not working? Lambda P of A. Okay, so so if A has to be a unit here. Similarly, we have exactly the same properties in the ring O star. ABT is equal to 1 if both A and B are units, and if A is a unit and T is what is called a uniformizer, right? So a uniformizer, we have already defined it in QP maybe, if you recall what it is, but a uniformizer is something whose valuation is equal to 1. So that was also the definition for VP, or in QP as well. Uniformizer in QP is an element whose valuation is equal to 1. So here, instead of T, you can take any uniformizer, because any two uniformizers will differ by a unit. And for a unit, it doesn't make any, you just expand it out. So what I'm saying is that if I had some B times T, where B is another unit, that's going to be a BT, a TT, and this is equal to 1. So this and this are really the same. So as I said, these two allow you to compute the Hilbert symbol in all cases. For example, let's compute this TT of T. So we had computed earlier PP at P, right? So here's the computation. I can write T as minus T times minus 1. And then by multiplicativity, I get this. And one of the properties tells me that this factor here is equal to 1. So I get this. And now I apply this second thing here. Here T is a uniformizer and -1, so it's, yeah, that's what's written here, and so that's equal to 1. Yeah, so it's, I should have written lambda k of -1 in between. From here, it's lambda k of -1, which is to say it's equal to 1 if this -1 is a square in k star, and it's -1 if -1 is not a square in k star. And you can check that it's a square if and only if q is congruent to 1 modulo 4 and so on, right? So these three cases, 1, 2, and 3, this is number 3, this is number 1, number 2. These three cases allow you to compute A, B, T in all possible cases. Cover all possible cases, right? So here is now the important property which has the name of Steinberg attached to it. It says that if A plus B, if A and B are 2 units, it should be, yeah, K star. They don't have to be units. There have to be any non-zero elements of K. If their sum is equal to 1, then this ABT is equal to 1. So as earlier, we can prove it by a case analysis. So up to interchanging A and B, either the valuation of A is strictly positive or it's strictly negative, or both the valuations are equal to 0. So the proof is really similar to what we have done earlier. And you should, so let's consider this case, for example, right? Now B is equal to 1 minus A. And A, the valuation of A is strictly positive. So this B has to be in U1. And everything in U1 is a square, right? So ABT is going to be AC squared of T, and AC, which is AC whole squared, and which is equal to 1, because plus minus 1 whole squared is equal to 1, right? So let's look at this case, the next case, when the valuations of both these things are equal to 0. So maybe we have already, yeah, we have already seen this case, right? That was the case 1. We said that if you have 2 units, then yeah. Oh, wait a moment. Yeah, so here you will have AB T equal to 1, even without the hypothesis that A plus B is equal to 1. What we are proving is that A plus B equals 1 implies that A comma B T is equal to 1. But if A and B are both units, I don't need this hypothesis. I still have this thing if they are both units. And P is different from 2 as here. Okay, so let's look at the case VT strictly negative. VT of A is strictly negative. The valuation of A is strictly negative. Then you can write A as T to the minus n times U, where n is strictly positive and U is some unit. Then there are some subcases. Either this n is even or it's odd. And if it's even, you can multiply A and B by T to the n because it's a square. When you multiply these two things by squares, you don't change the value of this Hilbert symbol. So when I multiply them by T to the n, I'll get this here. Now you have both of these things are units. So this Hilbert symbol is equal to 1, right? That's it. If the valuation of A is odd, then n plus 1 is going to be even. So T to the n plus 1 is a square, and I can multiply A and B by T to the n plus 1. So I'll get ABT equal to this. Yeah. So this is what A is equal to. This is what B is equal to. Now I multiply them by t to the n plus 1, I'll get this here and this here. Then I can expand, this is a product of two things, t and this thing. So I'll get this, I'll get 4 factors, 1, 2, 3, 4. And now you apply the definitions. This is lambda k of u. This is lambda k of minus 1. This is always equal to u because both of them are units. And this is lambda k of minus u because the reduction of this modulo t is minus u. So what you will get is lambda k of u times lambda k of minus 1 times lambda k of minus u. Now lambda k is multiplicative, so this is equal to the lambda k of u squared, but u squared is a square, so lambda k has to be equal to 1. That's it. So what does this prove? This proves that if A and B are two elements whose sum is equal to 1, then the Hilbert symbol ABT is equal to 1. This is the Steinberg property. Okay. Now here is an important result, which is analogous to what we had done for QP. It says that ABT, take any elements, any two elements A and B in K star, and the Hilbert symbol is equal to 1 if and only if there exists x, y in K satisfying this equation. Ax squared plus by squared equals 1. So this direction is the easy direction. If x and y exist, then, satisfying this, then if your x is equal to 0, then if x is equal to 0, then this b has to be a square, right? B is a square, and therefore this Hilbert symbol is equal to 1. You are done. Similarly, if y is 0, then A is going to be a square, and the Hilbert symbol is equal to 1. If both of them are non-zero, then I can multiply A and B by these squares without changing the Hilbert symbol. And now I apply this fact which I've just proved, that if the sum of two things is equal to 1, then the Hilbert symbol is equal to 1. That's what I'm using here to conclude that this is equal to 1. So this implication has been proved, and now we have to prove the other implication, this one here. So as before, this is really similar to what we had done for QP. So there were so you're allowed to interchange A and B because ABT is the same as BAT. And also this equation has a solution if and only if this equation has a solution, right? Completely trivial. We can also multiply x and y by squares. It's not x and y, it's A and B. So you can do it without changing the Hilbert symbol. This we already seen. And if this equation has a solution, then when I multiply A by c squared and B by d squared, then it continues to have the solution. If it has a solution xy, then the new equation with the coefficients ac squared and bd squared will have the solutions x upon c, y upon t, right? So this is not very exciting. So using these two facts, that I can interchange A and B, and I can replace A by AC squared, B by BD squared. These reductions allow you to just consider these three cases. The valuation of A, the valuation of B is either 0, 0 or 0, 1 or 1, 1. Actually, this last case can be reduced to the case 0, 1 by replacing A by minus A times B inverse. Of course, you need to check something. You need to check that the Hilbert symbol doesn't change when I replace A by this. and the existence of x and y doesn't change. What is this? Yeah, doesn't change when so there exist x and y satisfying this equation if and only if there exist w and z satisfying this equation. That's what we need to check. So here's the checking for the first one. This Hilbert symbol, I just expanded by multiplicativity to get this here. And then I can multiply this by b squared to get this here, but this is always equal to 1. So it's this Hilbert symbol is equal to this one. Similarly, if there exists wz satisfying this equation, where the coefficient is this one here, then we have seen that if such an equation has a solution, then the corresponding homogeneous equation has a solution. This is the corresponding homogeneous equation, right? The homogeneous equation has a solution different from 0, 0, 0. Now you multiply this equation of course can be multiplied by b and you just rearrange, then you'll get a solution different from 0, 0, 0 of this equation. af squared plus bh squared equals bg squared, bg whole squared. And now you dehomogenize and you get this equation. So you have a solution xy to the equation ax squared plus by squared equals 1, if and only if you have a solution wz to the equation minus ab inverse w squared plus bz squared equals 1. But what does that do? What is this replacing a by minus ab inverse? What does that do? Here the valuation of a was equal to, yeah, so we were looking at which case? We were looking at the case, the valuation of a and b were equal to 1 and 1, right? We were looking at the case vp of a comma vp of b equals 1, 1. If I replace a by this, the valuation of a is 1, the valuation of this is going to be 0. So the case 1, 1 is reduced the case 0, 1. So I just need to consider two cases, right? The case 0, 0 and the case 0, 1. Okay, so here is the case 0, 0. It's exactly what we have done in the case of QP. You consider S to be this set consisting of A bar times all squares in the field K, and T to be the set 1 minus B bar times all squares in the set in the field K. Each of them has exactly Q plus 1 by 2 elements. That's because there are Q minus 1 non-zero squares and then 0 is also a square, right? So that gives the Q minus 1 by 2 elements, I mean non-zero squares. That's the number of non-zero squares, and this counts the 0 square. Okay, so now what happens if you have two subsets A and A of, let's say, K and B in K, if the number of elements in A plus the number of elements in B is strictly greater than Q, then, of course, this intersection cannot be empty, right? Because K has only Q elements. There's no space for two disjoint subsets which have strictly more than Q elements. So here are these two subsets. The number of elements in each one is Q plus 1 by 2. So the total number of elements in them is, and of course they are disjoint, right? I mean, these two are disjoint. So the total number of elements is Q plus 1 on disjoint. What am I saying? Forget about being disjoint. Now, these two subsets have q plus 1 elements in total, but there are only q elements in the field K. So there has to be at least one element which is common to these two sets. They are not disjoint. I mean, that's exactly what I want to prove, that they are not disjoint. If they were disjoint, it would be a contradiction. So they are not disjoint, and therefore there are x and y such that ax squared plus by squared is congruent to 1 modulo t. A common element will be, so there's a psi and there's an eta. So there's an x whose image is this psi, and there's a y whose image is this eta. And a bar psi squared is equal to 1 minus b bar eta squared. This is exact. So the exact translation of this is this here. Ax squared plus by squared is congruent to 1 modulo t. And there's another way of saying that you just take this x squared to the other side, and that's it. Now, if there are two possibilities, if x is 0 modulo t, if it's congruent to 0 modulo t, then this thing is a square in, I mean, then it becomes a square modulo t. I mean, if it says it's 0, then it's a, sorry, wait a moment, what am I saying? If it's not 0, yeah. If x is not 0, congruent to 0 modulo t, then this thing is a square modulo t here, and therefore it's a square in O star. And then I'll get this equation. So there is a pair that this equation has a solution. On the other hand, if x is congruent to 0 mod t, then that shows that, where's the equation here? Here's, if x is 0 mod t, then I get b is a square. Then b is a square modulo t, so it has to be a square in O itself. And then I get this solution. So what were we proving? We were proving the case when the valuations of these two things are both 0, both of them, a and b are both units. And so now let's consider the case when a has valuation, a is a unit, but b is the uniformizer. What is the hypothesis? That this Hilbert symbol is equal to 1. And what do we want to show? We want to show that this some equation, the equation ax squared plus by squared equals 1 has a solution. Now, if this is a unit and this is a uniformizer, then the Hilbert symbol we had computed, it's equal to lambda k of that unit, right? That's what we have seen earlier. And by hypothesis, the Hilbert symbol is equal to 1, which means that the lambda k of a is equal to 1, which means that a is a square. So there's a z such that a is equal to z squared. And then I just take x to be z inverse and y to be 0. And I get a solution xy to the equation ax squared plus by squared equals 1, right? So, oh goodness, I have only 6 minutes left, but let's continue, okay? So, for any b in k star, I denote by lb the extension of k obtained by adjoining a square root of b. So, of course, this is equal to k itself if b is a square. In any case, I denote by nb the norm map from LB star to K star. It's just the identity map if B is a square. And it's the map which sends x plus y root B to x squared minus by squared if B is not a square. And here's the theorem. Take any two elements A and B in K star. their Hilbert symbol is equal to 1 if and only if A belongs to NB, to the image of the norm map from LB. Remember, LB is this when you are drawing square root of B. And so you see, this is somewhat funny, because this Hilbert symbol is a symmetric condition in A and B. Whereas this doesn't look like a symmetric condition at all. So there's one nice corollary of this, which is that A is a norm from LB star, if and only if B is a norm from LA star. That follows from this. Once we have proved this theorem, it follows from the symmetry of the Hilbert pairing. So there's absolutely nothing to prove if B is square, because in that case, the Hilbert symbol is also equal to 1, and the extension LB is also equal to K. So everything is a norm, of course, because the norm is the identity mapping of K. So there's nothing. Now, that's the only case to consider. B is not a square. Then ABT is equal to 1. What have we proved? We have proved that ABT is equal to 1 if and only if there exist XY satisfying this equation. And earlier we had proved that there exists XY satisfying this inhomogeneous equation if and only if there exists FGH different from 0, 0, 0, satisfying the corresponding homogeneous equation. This equation is obtained from this one by homogenization. Now, this equation can be manipulated to this one. I mean, can be dehomogenized to this one. So this homogeneous equation has a solution if and only if this corresponding inhomogeneous equation has a solution. And that's exactly the same as saying that A is a norm from LB. Because the norm map from LB will send W plus Z root B to W squared minus BZ squared, right? There's a norm map from LB star to K star. Okay, so well, another corollary of this result is that for every quadratic extension, the index of the norms from E, the quadratic extension is E, the norm map is from E star to K star, the index of the image of the norm map is 2. Why is that a corollary? Now, so that's a corollary because we have, well, I think we have to go back and say something more. Yeah, maybe it doesn't follow immediately from, oh goodness. So you have to wait another few minutes till I can share my screen again. Can you hear me still? Hello? Yeah.
Yes, we can hear you.
Yeah, okay. Yeah, there's some Wi-Fi problem and you're going to see the screen again. Yes. Okay, so we were looking at this corollary. Maybe it doesn't follow from what we have done, but it will follow later after we have proved the next theorem. Okay, so let's recall what we have done. We have determined the structure of K star modulo squares. It has a basis consisting of two elements, U and you can take T or minus T, makes no difference. Any uniformizer would do, right? So minus T is also a uniformizer. So it's more convenient to take minus T for what I'm going to do next. So U is a unit, which is not a square. It's the same as saying that lambda K of U is minus 1. So K has precisely 3 quadratic extensions because there are precisely 3 non-zero elements in K star modulo squares. And those are U minus T and minus UT. So the quadratic extensions are K root U, K root minus T, K root minus UT. And we have also seen that this K star has precisely 3 quadratic characters, nu T, lambda K, and nu T, lambda K times lambda K. So this is just the definition of nu T. This is the definition of lambda K, as this nu T was this composite, lambda K was this composite. So there are 3 on the left-hand side and 3 on the right-hand side. There are many possible bijections between a set consisting of 3 elements on the left and 3 elements on the right. But there's only one bijection which has the property that if the quadratic character chi corresponds to the quadratic extension E, then the kernel of chi is equal to the image of the norm map from E. And that's the bijection given here. This bijection here, this bijection, that's the one which has the property that the kernel of this quadratic character is equal to the image of the norm map. Oh goodness. So I'm running out of time and I don't want to keep you detained. So maybe we'll pick up from here next time. It'll not be a bad idea for you to think about this, about how to prove that in each of these 3 cases, the kernel of chi is equal to the image of the norm map. Okay, so we'll stop here today and we meet on Monday and there's a tutorial on Friday. Are there any questions? Yeah?
Sir, is there any Hensel lemma type thing in this setting?
Yes, there is.
Okay.
Yeah. For this, there is a, and probably we will see it later. So there's a Hensel lemma in a more general setting than what we have seen for QP and even for these fields K. Even more general settings are allowed. So it's valid in, for example, fields complete for a discrete valuation and so on. We have not introduced those concepts, but yes, it's a much more general result. These are very special cases.
So in the tutorial on Friday, I'm going to continue with Hensel's lemma. So maybe, so I'm planning to touch upon, briefly about the general, for the general fields.
That's a good idea. Yeah.
Yeah.
Field complete for a discrete valuation, or you allow the valuation to be arbitrary, or?
No, I will just introduce what are Henselian fields. So.
Okay.
Yeah.
I see. Good. Right. Other questions? If there are no further questions, then maybe we'll end the session today and see you on Friday. Okay. Yeah. Bye.